All right, so let's build our model. So first of all, we are dealing with this model. We have to construct our matrix P. So let's construct the matrix P. We already actually constructed it on the blackboard, so I will just simply write here what we have on the blackboard. So the first row of the matrix will be 0, 1/2, 1/3, 1/6. Second row, I think I will even teach you how to continue a line in Matlab using the amazing 3 dots syntax. 0, 1/2, 1/4, 1/4, amazing 3 dots. Then we have this 1/4 several times. I recently heard a very good tip from one student, because to me, you know, I grew up with books and I studied with books. Learning from videos, it's quite new to me. But then I heard, so I learn all the time new tricks about that. This may be very known to you all, but I heard this one tip that watch the video with a 1.5 speed. You can still understand the talk and it's faster. This really works well with these screen capture things, actually, because here, maybe the talking is not so important if you want to more see what kind of code comes up. I know maybe this is really basic stuff for all of you, but you know, I'm a dinosaur, so I'm learning new things in this digital field all the time. Oh, much more beautiful with indentation. So let's. All right, so I think we have now painstakingly constructed our Markov matrix. Let's still check that it works. So if I run this thing and let's see what is our P, looks okay to me. So then we can start trying this. What should we have? Okay, so first of all, let's assume that our situation at day 0 is just an equal division of customers between 4 companies. And then we compute the next day formula by the matrix multiplication. And let's try that first. So initial market shares, let me call this x0, and we'll put here like this, and market shares after 1 day. I call it x1. So we have x0 multiplying our matrix. So let's see what happens. Well, something like that. Hard to say yet what's going on. We will see something maybe surprising soon. So that was just one step of this process we describe in our model. The idea, of course, is to compute also the second day, which is now the day 1 times the matrix. And given that day 1 is given by this formula, we see that actually our matrix appears here twice. And actually we can see that we can use matrix power to express the nth day situation by p to the power n. So after 1 day, after 2 days. Let's see how this looks like. After 2 days, I don't know if we can really say much about this, except that the crowd at TNT is not very big, although after 1 day it was smaller. After 2 days, TNT has more, although all the customers exit every day from that company. Now, maybe the most important point in this computation is actually not to bother with this, doing this like one by one. We can use the power notation. Market shares after n days. So we can put n, for example, 10, and xn equals then x0, which I hope I still have there. Yes, as x0 times matrix P to the power n. Okay, let's see what happens. It seems that this is not changing so much anymore. These things still changed, but let's actually take a look what happens if we compute with, let's put 100. So you see, between 10 days and 100 days, there is not so much difference. This is almost the same. Here also, the first significant digits are the same. Also here, also, they're very close between 10 and 100 days. So it seems that not so much change happens anymore after 100 days. We could also take a look at more digits. With this command, we will see more digits. For example, now if I want to see what is xn, we see more. So let's try now what happens, let's say with, with 200 days. What is the difference between 100 and 200 days of this process? So this is after 100 days. So we have actually it's completely the same up to computational accuracy. Here it seems to be that only the machine epsilon is different between 100 and 200 days. These are completely the same. Here, well, in this level of 10 to the minus 16, there is some little difference, but in numerical computations, that's really, I mean, that's not reliable information. That comes from floating point rounding errors. So it seems that our model is finding some kind of equilibrium state, or it kind of goes, it doesn't change much after some while of this market behavior. How about if we have a different starting point? If we compare after 100 days and 200 days for a completely different initial market shares. Let's change this one. Okay, any suggestions, please? First market share, please. A number between 0 and 1.
110.
Sorry?
110.
Okay. Okay. Some more. There. Second row, third row. Now it needs to be not too big. Please throw something. How much? Okay. like this, and then actually I think I have to make sure that it sums up to 1. Let's do it this way. Let's see. Let's see if this works. Okay, looks nice. And now let's compute with this one. So after 100 days, we have this situation, and let's compare to after 200 days. We observe that again it happens that there is really no difference between, or well, extremely small difference between the situation after 100 and 200 days. And moreover, these numbers are the same that we had here. So it seems that regardless of our market share at the first day, the whole process will converge to the same equilibrium state. So I will put into the exercises for you some stuff to compute a little bit to observe this phenomenon. This is something that's typical for this kind of Markov models. And then of course we can question how realistic is this? Is it a good feature of our model of market shares? What's wrong with it? I mean, if the world would really work this way, then everything would just converge to a stable situation. But that's not the case. Any thoughts? Tuleeko jotain kysymyksiä tai kommentteja mieleen tästä kummallisesta suppenemisasiasta? Mitä mieltä olette esimerkiksi siinä, onko realistista, että meillä on sama asia tapahtuu joka päivä? Ei. Mitä sille pitäisi tehdä? Tai voisiko sitä jotenkin muuttaa? So for maybe a couple of thoughts. We have very little time left. So one thing is that I think it's unrealistic to think that the situation, the market dynamics would stay the same indefinitely. I mean, there may be new companies coming in, or one of these going away, or maybe the customers will behave differently. Maybe there are new advertisement campaigns that change the behavior completely. So it's again good to understand that we have a mathematical model here that works perfectly in its own ideal world, and we can analyze it and see its properties. But then we have to be careful that not to think that this will describe the world until the end of time. But still, this may be useful. Let's say if we know the situation and we know this information, maybe it's good for like 2 weeks or so, or maybe like a couple of months. But maybe it's good to keep in mind that we shouldn't use the same model for too long, because then it will lose its descriptive power. And one idea could of course be that the matrix is updated once in a while, but then it's good to remember that then the chain is not anymore a Markov chain. In Markov chain it's important that the next step in the chain only depends on the previous one and not on the history. If we have a changing matrix, that's not true, and the Markov theory is not anymore valid. Okay, that's our first example of a little mathematical model. I hope you enjoyed. I will upload the stuff to the website and see you next week.